We can extend that second fundamental theorem of calculus a little bit further, by the way, by treating this as an expression that could contain another expression. Kind of weird, but let's think about it. In our our second fundamental theorem of calculus, we evaluated on an interval I that contains some value a and some fixed endpoint, or well, some unknown endpoint x. Well, what if that endpoint changes not at x, but at some function u of x? What will happen? Well, when we take the derivative of that expression, which would be the definite integral from a to the function u of x of f of t dt, the derivative would be f of u of x times the derivative of u of x, essentially an application of our chain rule. Well, let's talk about that right here. We've got f of x, the antiderivative of f of x, being the integral, definite integral from pi to x squared of the function sine of t dt. What should we expect? Well, again, when we say let's find the derivative of f of x, capital F of x, that means that we're actually looking for f prime of x. We didn't say f prime of x, but we said f prime of x by saying the derivative of the antiderivative f of x. Well, that is going to be, by our version above, the derivative with respect to x of this quantity, which contains the definite integral from pi to x squared of sine of t dt. All right, so how should that look? Well, by our rule above, this is going to be equal to the function sine of the quantity x squared times the derivative with respect to x of x squared. Now, we could actually say x squared minus pi, but at this fixed endpoint, its derivative will be 0. And so our result right here will be f prime of x equaling sine of the quantity x squared times 2x, or stated another way, equaling 2x times the sine of the quantity x squared. So that is the derivative of f, capital F, of x. Well, that's just what we wanted, and so we're done.